Good morning, everyone. My name is Caleb Price, and today I'll be talking about building an AI golf caddy using a physics-informed neural network. So just to provide an outline of this presentation, I'll first talk about the motivation behind this work, and then discuss some of the methodology that was used, including data collection, the design process, the system structure, including all the moving pieces, the neural network, and finally the simulator. And then we will go over some of the results. Those will include the simulation results as well as performing tests on 5 different holes. And then we'll just conclude with a few concluding remarks. So as far as the motivation for this project, I'm actually graduating in a couple weeks, and so my research is already complete. And so I decided to do a different project, one that was a little more fun. So I decided to build this AI golf caddy. Just to give a background of golf, I'm sure most of you know, but in golf, basically the way it works is there's 18 holes shown by this picture over here on the right. And the goal is to be able to hit the golf ball into the hole in as small amount of strokes as possible. In order to help you do that, you have different types of clubs in your bag, and those are shown over here on the bottom right-hand corner. And basically, different clubs can hit different lengths and different heights. I won't go into the details too much, but just know that depending on the club you select, it will affect how far the ball travels. And so in real golf, they have what's called a golf caddy. This is the guy that follows the golfer around the course. And basically, he's just telling him what to do, what club to use based on the current situation. A human golf caddy costs about $100 per round or $40,000 per year, which is pretty expensive, much more than what I can afford. And so today I'll be trying to build a AI golf caddy. And the cool thing about this is that it can utilize every swing from my past history and use that to make the next decision. And it can be trained on specific golf courses and specific scenarios. And the end goal is that this will be much cheaper than hiring a real caddy. And so the first part in this process is to go and collect actual data. And so I went to the Pure Golf simulator in Springville that uses the TrackMan simulator. It's a $15,000 simulator, so it's pretty dang accurate. And then I did 10 different swings on 8 different clubs shown in this list over here on the left. And then the results of those swings are shown over here on the right. And then this middle screen here, we're just going to have a video of what it looks like. So I select a club, I go ahead and swing, it does some computations, and then it prints the results here on the bottom of the screen. And then I reset and swing another club. And so over here on the right is the results of those swings. Each color corresponds to a different club. And you can see some correlation between my swings. So with the green club, I have a tendency to swing to the right, whereas with the light blue, I have a tendency to swing to the left. And with my driver in red, it's kind of just all over the place. And so the goal is to get the neural network to train on this data and be able to understand my tendencies when I swing. And so stepping into the design process of building this, some of the challenges that exist is one, it's not predictable which swing you will get. And so if we look at the colors up here, right, we don't know if I swing my driver, am I going to get the red dot way over here or the red dot over here on the left? The other challenge is that there's not a definitive good shot. When we've trained models in the class, we kind of give it input parameters, we get an output, and then we can tell it whether or not it was good. However, when playing a round on a golf course, you don't know if you hit the ball 200 yards. Is that good? Is that bad? It kind of depends on the hole. And really, the loss term at the end of the day is how many strokes it took you to complete the hole. And so that adds some complication. And then there's obviously the challenge of dealing with the hazards. If you hit the golf ball into the water, for example, that should be penalized higher than other strokes. And so I think the real way to approach this problem is to use reinforcement learning. I actually tried to do this for several hours and it proved a lot more challenging than I had originally thought. But basically with the idea of reinforcement learning, if you look at this golf course over here on the right, is we would just simulate every situation possible, swinging from every location until eventually it learns using a reward function, the optimal way to approach the hole. But like I said, this was very slow. I don't have any experience with this, and it was pretty hard to monitor the training because when training a reinforced learning network, it basically doesn't show any improvement until all of a sudden it spikes up as it finds the solution. The other option is to use a traditional vanilla net. However, I don't have enough data considering I only have 100 data points, 10 points for each club. And as I mentioned earlier, it's hard to define a good shot. And so the way to get around this is basically to use a physics-informed neural network. And so here's kind of the ending methodology that I decided to use. And so here we have the system structure. And so here on the left, we have the inputs, which is represented by the current ball location and the hole. We then have the neural network, which is going to decide which club to use and how hard to swing it. That gets fed into a swing simulator, which takes into account that data that I retrieved during that simulation that I showed earlier. And then that swing simulator will predict, based on the club selected and previous data, where that ball is going to end up, which then gets ran through a loss function and gets trained over and over again. And as I mentioned earlier, one of the challenges is we can't just do this for a single swing. We have to do it for the entire hole. And so basically, we have a loop here that just continues to run until we land within 30 feet of the hole. And I'll talk a little bit more about that later. I had to build several classes in order to make this possible. I won't dive too much in details here, but basically, I had to build like a course that has holes, hazards, and players. The player keeps track of the ball location, and then all of this gets fed into the simulator. I also built a Pygame simulator to kind of help debug, and it kind of gives a cool way to present the results at the end. As far as the neural network, it has about 16 inputs, or it has 16 inputs. These include both the X and Y location of the ball in the hole, and then two corners to represent a square for three separate hazards. If I only had one hazard, then I just zero filled the rest. As far as the neural network itself, it has three hidden layers with a width of 32, and then I use the CLU activation function. And then I also had to use layer normalization because one of the challenges is when you have that feedback loop that I showed earlier, you actually have more hidden layers than you originally think. The reason for that is usually when we run through the neural network, we then call zero gradient and like reset the weights and biases. However, that doesn't happen here because we run through the neural network multiple times. And so as we unroll that loop, we basically have more and more depth. And so I definitely struggled with vanishing gradients. And so I had to add this normalization layer to get rid of that issue. And then the outputs of the network are 8 club logits and a power percentage, how hard to swing the club. As far as the swing simulator, the inputs, so we have the selected club, or we have those 8 widgets being passed in, and then we perform a softmax on those clubs to decide which club to swing. And then we have the power percentage, which is how hard to swing. And so basically, you can imagine it like this. If I have this ball over here on the right and we're aiming towards the hole, in a perfect world, we would get this black line right here as far as where the ball would land, but then that gets adjusted by the power adjustment parameter, and then that gets shifted to the left or the right based on the input data from the simulator that I went and swung at. So this is kind of the user data that's coming in and affecting the shot. And then the final output is that new ball location. And then in order for the loss function for this to work, so the first obstacle to overcome was getting the simulator to hit the ball far, or getting the model to predict to hit the ball as far as possible. And so the way I got around that was adding a loss term for the remaining distance. And this basically just sums up how much distance is remaining after each swing. I then had to add a penalty for hitting the ball out of bounds or hitting it into a hazard. And it really did take me a long time to balance these weights and get it to hit the ball correctly. For example, when I put the incorrect weight on the out of bounds, it would cause the model to just predict hitting the ball about 10 inches over and over again. And so we weren't making any progress. Once I got those balanced, we were able to finally get the simulator working. And so here I have just some of the results of that. And basically what we have going on is over here on the right, I have the loss function. So we have the training data in blue and the test data in orange. The test data is basically just shifting the ball to a different position and making sure we're not overtraining. And then here on the bottom left is an example of the actual simulator. And then on the bottom right, I have just what it kind of looks like while it's training. And so on the very first epic here, we see that it predicted something that required 8 swings, which is pretty bad. And then after 250, it got down to 3 and down to eventually 2. So if we go ahead and look at the result of the first hole, this is simulating the most basic situation where we're basically going to just swing once and aim at the target here. So if we go ahead and run that, we can see that it in fact does manage to hit the ball within 30 yards. And we can kind of see the training and loss data over here. And then the output is, it's telling us for shot 1, use club 4 and swing at 70%. For hole number 2, we once again have no hazards, but now we have to hit it extra far. So this should take more than one swing. We go ahead and simulate that. Sure enough, we get a full swing of the driver and then a minimal swing of the second club, which is demonstrated down here. And then we have the results, or the training loss function, or loss results up here. For hole number 3, it's basically doing that same test previously, but now we've added a water hazard. And so it should still hit the driver, but, or it shouldn't hit the driver. It should hit it short of the water and then use another club to get the rest of the way. Sure enough, it hits it short and then it hits a longer shot. And we can see the results over here on the bottom right. And then this hole, it should choose a club that swings to the right, which it does, and then it reaches the hole here. And then we have the lost data once again, and we can see the two clubs that it selected over here on the bottom right. And then for the final test is it shouldn't hit it left, it should go right, but it's going to have to hit it short and then hit a longer shot. And once again, we see that it works. It goes ahead and hits it short of that hole or the water and then makes it to the hole. So just in summary, we were able to successfully get or I was able to successfully get the simulator to work on 5 different holes. I was able to avoid hazards and out of bounds, and I was able to do this by building a physics-informed neural network. Things I learned along the way, it was pretty hard to get things to work with that feedback loop, and one of the main problems was making sure everything worked well with backpropagation, including putting a requires grad on all my variables and making sure that all the functions would work in backpropagation, as I mentioned earlier, with the balancing of the weights as the loop was unrolled, and then just using softmax rather than argmax to make sure I retained all that information when calling the backpropagation. And for future work, I would suggest using reinforcement learning for this project. That way we can include a little bit more randomness in the swing simulator. With that, that is my project.